Ladies and gentlemen, this year TNC cannot start without a sad remembrance, because, as many of you know, this year on the 23rd of February, our Secretary General, Carol Fitch, passed away. And Carol has been in service for TERENA for many years. After 2 years of very serious illness, unfortunately, he's not with us anymore. He has done really a lot to TERENA and to our community. And as his successor, I have the weight of, remembering him at the start of this event. I would like to honor his memory, asking for 1 minute of silence to remember Carol at the beginning of this conference. Thank you. But there is also some very positive legacy that Carol has left to us. Not only, our community, TERENA, the way TERENA is. One of the things that he wanted, and he instructed the notary in his will, is to establish the Fitch Foundation. This is a charity which manages his legacy, and he wanted that to help the promotion of innovative projects and ideas for the advancement of research and education networking. So that foundation has been automatically established on the day of his death. There is a board of which I happen to be the chair, together with my colleagues John Dyer, Bert van Pinksteren, and Carol's sister Antoinette Fitch. We have given instruction by Carol for administering the money and helping with some financial contribution to, as I said, innovative developments, etc. And also by giving annually a prize, the Fitch Medal. Carol wanted this to be given at a prominent networking event. It could be TNC next year. So with this note, I'm happy to announce this. I think is a great thing that he wanted, for us to continue remembering his work, and with this I just pass the floor to the chair of TERENA for opening the conference and continue with the happy notes.
Thank you, Valentino. Even after his death, Carl continued to support our community. This is remarkable. I'm speechless. Okay, ladies and gentlemen, dear friends and colleagues, as president of TERENA, it's my duty, but also my pleasure, to welcome you here in Dublin and in this remarkable and beautiful campus. It is the third time that Ireland is hosting the conference since the creation of TERENA. If we consider the support to our annual event, HEAnet is the most active member of our community. This is a gentle signal to the others. So thank you, John, for your support and collaboration. Hosting the TNC starts to be a routine activity for Irish colleagues. They know perfectly well the requirements, the constraints, and the difficulties to organize this event. It's the first time I have seen Gyongyi so relaxed for a first day of their conference. So no doubt that they will make this week a complete success. The theme of this conference is networking with the world. The program committee has selected more than 130 speakers to cover a larger range of topics like cloud services for education, disruptive networks or business, software-defined networks and applications, network security and privacy, network strategy and development, all about network technology and innovation in a worldwide environment. But we may not forget another important value of the conference. I mean, people networking. This week, we are expecting more than 600 participants coming from 55 different countries, covering 5 continents. So let's talk to each other, let's exchange our visions, our experiences, let's define together our future. It is time now to network with the world. Before finishing this, my welcome, I would also say some words about the fact that maybe this is the last time that we are using the name TERENA for a conference. You are probably aware that we are working with Dante to restructure, to integrate both organizations in a single organization. And one of the impact of that process will be we will change the name. So don't worry if the next time we will come back with another name for the conference. But I cannot say much about that because we will have a general assembly this Tuesday and Friday, and we will decide to continue or not to stop the process. And finally, before finishing, I want to also thank the TERENA staff for the dedication and their professionalism to make the TNC the largest and the most prestigious European research networking conference. So, one word, enjoy the conference, and thank you. I'm inviting now on the stage our host, John Boland. He is the Chief Executive of HEAnet, the Irish Research Networks. John, please.
So thank you, Pierre. While we're very committed in Ireland to all this international collaboration, I didn't realize it was quite that scale. Now I know why I can't get anything done back at the office if everybody's working on all this stuff all the time. But first of all, I wanted to welcome you all here with a traditional Irish welcome. Céad míle fáilte go baile átha clia. 100,000 welcomes to Dublin and to Ireland. We're delighted to finally be here. Benjamin Franklin said that the only certainties in life were death and taxes. Well, in Ireland, we've got a few more things, like the weather. The weather is going to change, so don't worry about it, okay? And also the fact that you'll have a good time here. We can guarantee that. And so Pierre's call for people networking, there's no better place than Ireland to get on with a bit of that, I suggest to you. So, as I say, it's been 3 years in the planning to bring this conference here for us. It's been a great collaboration between John G. and the TERENA staff, between the HEAnet team, and great support from UCD here, the college IS services, where all the parallels will take place in the Sciences building, which is a brand new building. It's the first time it's ever been used for an event. It's just opened. It's built with the latest environmentally friendly stuff. So the glass is treated in such a way that it suppresses the mobile phone signals. So you'll be free for a week from all those calls and texts, okay? It's a feature. However, if you do need that old 3G technology, just step outside and all the operator signals are there for you. So, but as I say, it's great to have TERENA back in Ireland. We have some history with the community. As Pierre alluded to, back in 1990 in Killarney in the southwest of Ireland was a landmark meeting of a joint meeting of Rare and Earn. There's a few suspects here from that. Dennis Jennings is in the audience, Michael Nolan, Case Neggers, to name but a few. That was an important meeting because it formed the basis of setting up TERENA and forming it. In the sort of 20 years or so, Ireland has changed a lot. We often say that to a large extent we missed out on the Industrial Revolution, but we're determined to be part of the Information Revolution. And as you all know, we've been through tough times, we've been through boom and bust. I think the ship is fairly steady now, but we won't get carried away, promise. We have to take it steady. But through all that, we have been successful in IT terms. 8 out of the 10 global internet companies have their European headquarters here in Dublin. Intel, in March, a company who is at the absolute bleeding edge of IT technology and investment, they have selected Ireland to build the plant for the fabrication of their next generation of technology. They're going to invest €3.6 billion, about 20 miles from Dublin. It'll create 4,000 jobs in Intel and 4,000 jobs in the surrounding community. So it's very important that we provide the graduates, the educated, and the research to support all of these companies. So therefore, it's very appropriate to bring this conference here because we're all working on the future infrastructure and services to underpin education and research. So it's entirely appropriate. And indeed, coming to this university, UCD, University College Dublin is the biggest university in Ireland and one of the leading research universities. In a moment, I'm going to call on Professor Mark Keane to talk to you. Mark has been a former board member of HEAnet and has been an advisor to the Irish government on their investment in science and technology. And Mark will talk about the focus, some of the focus amongst the universities now in terms of research and what the ICT areas are. But finally, I wanted to say, I feel the hand of history on our shoulders here, folks, at this meeting. As I said, historically, there were some decisions made in Killarney that led to ultimately to the formation of TERENA, the Research Association, to Dante, the operational unit. An enormous amount has been achieved in this 20 years since that absolute decision was made. And I think now we stand at the juncture here in Ireland once again. We like a bit of history here. We stand at the juncture of maybe making significant progress, of bringing the organizations closer together and setting us up for the next 20 years of supporting education and research. So that's all in the background, as Pierre says. In the foreground, we've got this conference to get on with. It's a fantastic program been put together by the program committee. And so really, I just want to warmly welcome you once again to Dublin and wish you a successful and enjoyable few days here in Ireland. Thank you very much.
Hello, welcome to UCD. I have this sense of increasingly less important local politicians lining up to say things to the audience and people getting increasingly less interested in what they have to say. So I'm going to try and say something of more interest, hopefully. So I'm here just to give you, I guess, a quick overview on the context of UCD in Ireland and some of the research that's currently going on in the ICT space. Ireland, as you can see here, has about 7 universities. The dates after them are the dates of their establishment. And we also have a bunch of institutes of technology, which I haven't listed, including Dublin Institute of Technology, which is quite a large body. These universities here are rank ordered roughly in how they appear in international rankings. So as I looked at the list, I was reminded of something Steve Ballmer said at a talk here about 10 years ago. He was talking about Microsoft's position in, I think, mobile technology or search technology. And he said, the good news is we're number 2 in the market. And the bad news is we're firmly number 2. So we're in a similar situation here, although I think ICT and UCD is perhaps the national leader. Overall, Trinity has a very good name, and as you can see, a much longer history than we have here. So to talk a bit about UCD, the founding rector of UCD was Cardinal Henry Newman, who wrote a very important book about what he saw as the role of universities in society. It's often taken as a sort of paradigm, if you like, for the modern university up until recent days, sort of specifying exactly some of the benefits and important properties that universities should have. UCD has tried to contribute to Irish society in a major way. It's probably a dubious thing to say that most of Ireland's leading politicians came from here, but I guess what we'd like to say is that some of the leadership of the country has emerged from here. It's a very large university, sometimes I think way too large. If you look at the French system, sometimes they split the sciences from the arts. We have about 5, 6, 7 major faculties that really cover very different areas. So there's about 30,000 students here on campus, which is really like a small city. And we have about 2,000 PhDs at the postgraduate level. The rest would be taught programs, master's programs. So there's a large research cohort that we're working over. And we have overseas campuses too. Since 2000, we've been teaching a software engineering degree in Shanghai in China. We also have campuses in Singapore and in other parts of the East. To talk a bit about some of the research priorities, because we're a very large university with very diverse research backgrounds, we cover quite a large number of areas, but the recent thing that's been happening about in the last, I guess, 4 to 5 years is that ICT is actually at last being put at the center of that. When I came here initially, many years ago, I had to argue very strongly for computer science. And of course, part of the problem is the younger a discipline is, the less it's recognized, right? But we've now reached a point where the university is very seriously considering putting data analytics, in this case is the name given to it, but essentially ICT at the very heart of the diverse areas in which we work. And of course, as people with this sort of background, you won't find this a surprise. The extent to which computing, ICT, technology has, in some senses, invaded our lives is probably has reached a level which we didn't imagine 20, 30 years ago. Certainly I didn't. When I look at what my daughter is doing on a daily basis, she now has contact with technology in a way which I couldn't have imagined, really. So some of the areas, just to give you some of the scale, in the health area, we have a very big institute called the Conway Institute with about 500 researchers or so, and significant research income coming in over the last few years. The thing I'll point out in this is within each of these areas, it's interesting to see the ICT coming through in the different names, like systems biology. There's a large effort in that area, and the future of IT and medicine being another one, for example, and connected health as well. We've done a lot of work in sensing for the last 10, 15 years or so. Similarly, in the environment, we have an Earth Sciences Institute that has, again, a very large component in the ICT area in terms of smart infrastructure and things like that. But I'm here to talk about the centre which has recently been established, which is this sort of data analytics hub. So I started doing research in aspects of sensor networks about 12 years ago, aspects of data analytics as well. And part of the problem was we didn't have a name for it. In fact, we found it very hard to get money for it. because there wasn't an aim. So we were saying things like, well, we're dealing with sensor networks and we're trying to deal with the amount of information coming out of them, and we're trying to optimize them for life in an environment and things like that. And people just didn't get it. You know, we had to describe individual systems, and people would say, well, that's just a system. I don't know what the deep coherent bit to all of this is. And of course, the deep coherent bit was the hardware and software technologies that sat beneath the system. And finally, we have a name for it, and now people are giving us money. So we recently established this very large center here called Insight. It's actually the single biggest investment in a research area in the whole country. It's 88 million over 5 years or so. It has about 200 researchers, and most of the third-level institutions of worth in the research space are partners in this. We also have a very large industry focus and collaboration within it, and we have multinationals in that, like Microsoft. We have large indigenous companies, for example, in the media area, like the Irish Times. But we also have lots of small SMEs as well that we're trying to help in various ways. And to look generally at what our focus is, I won't speak about all the details of this, but we've split the space up largely into the connected health area and then into the discovery economy, as we call it. So on the health side, you're looking at things like, you know, personalized medicine, disease progression, rehabilitation, and areas like that. On the discovery economy side, you're doing things like data analytics for governmental decision-making, say policy, evidence-based policy making, or indeed aspects of the future of news and media, which is one of the areas I work in. As we all know, traditional newspapers are under huge pressure at the moment, and it's not clear where everything is going, really, with respect to what they'll do in the future. Just to give you some sense of a little bit more detail of that, one of the things that struck me as I was thinking about it was that a lot of the challenges which emerged, I think, in networking technologies are now sort of working their way out into what you might call more conventional everyday technologies. So one of the things we're dealing with in this center is very large data sets. So you're talking in terms of hundreds of gigabytes of data in a given case that you're working with. So I remember years and years ago, you know, you'd think 1 million was a big figure, but it's not a big figure anymore. And, you know, you're dealing with, say, analyzing documents like a Twitter stream or something like that, or a set of documents coming in from a social networking site, and you're dealing with 100 million of those things. And of course, the emerging thing, which has become a big issue, is how do you do that in a streamed context? So people have developed technologies to do this sort of analysis when everything is sitting nicely in a database, and you know where it begins and where it ends, and you can develop metrics based on that. But in the streaming context, you don't know what's coming next. But you want to do something like machine learning over that stream in real time, and you're dealing with hundreds of millions of items as you do that. So it's a very sort of new environment in a sort of text analytics context, but from a networking context, it's really quite familiar, I guess. And one of the things we'll do in this center is we're going to build on different units, and just in the last week we heard of another level of funding of 5 million or so to look at specifically at aspects of analytics in the network context. So I asked the researchers in this area to give me some pictures, and they gave me this picture, and I don't know what this picture means, but I think the key aspects to it is it says things like video metrics and network level metrics, and I guess the point of it is that a lot of that data is going to be extracted at points in the whole network where normally in the past it wasn't extracted. And they also gave me some words to say that I hope mean something to you, because I don't know what they all mean, but the essence of it, I guess, is just that, I remember years ago hearing Cisco talking about putting artificial intelligence into the network, and I thought that sounded like a scary idea, you know, because most of it didn't seem to work very well. But the essence of this is to put more data analytics into the different parts of the network, and obviously then to do more personalized delivery or more smart delivery of what's going to the network at different levels. So I've tried to give you a bit of science, I've tried to give you some local color, and I'll quickly get off the stage, and thank you all for being here, and I hope you enjoy the conference. Thank you.
Thank you, Mark. It's a kind of introduction for the next speaker. You spoke about biology, ICT, and big data. So now we can start with the first keynote speaker of this conference, Barend Moms. Barend is a scientific director of the Dutch Tech Center for Life Science. He's also a professor in biosemantics. He tried yesterday to explain what is biosemantics, but it took half an hour at the Leiden University Medical Center. The title of his presentation is Fair Data, Science or Fiction. Barend will help us to rethink research by giving us insight into future research based on big data and the new responsibility and demands that come with that development. So, Barend, you have the floor. Thank you.
Thank you. Thank you, Mr. Chairman, and thank you for inviting me as a non-techie to this very impressive meeting with so many people. I was asked to give you an idea about data stewardship. That's one thing I will talk about in the area of big data. But before I start, I want to say that I'm not very familiar with computers and networks myself, although I'm in the Netherlands Bioinformatics Center. But I leave that to others. So frequently biologists like me, they leave these things under the hood and we expect them to be there, which is not always the case. And we will expect big things from you guys in the future. But one thing that we also can experience today is in this very complex world, we need respectful collaboration of specialists. So don't expect me to say anything sensible about computers, but also try to take what I say seriously when I talk to you from the biology perspective. So as was said, I'm a professor in Leiden University Medical Center, and my big passion is knowledge sharing for my whole life. My statement is always, knowledge is like love, it multiplies when shared, and many other things you have to, when you share them, you get less, both of you. So we started this new thing, the Dutch Tech Center for Life Sciences, where both universities I'm affiliated with, also Erasmus University Medical Center, are affiliated to as well, but 37 other partners in the Netherlands now. And I'm also the Life Sciences Integrator in the Dutch eScience Center, and most of what I will talk about today is actually eScience in biology. Then I'm also the head of Node of Elixir, the Data for Life infrastructure in Europe. Data for Life in this case is the tagline of Elixir and stands for two things, not only life sciences data, but also for life. So data should be there essentially forever as long as they are reusable. And that's part of the FAIR principle that I will tell you about a little bit later. I'm also one of the founders of the Open Facts project, the Open Pharmacological Concept Triple Store, which I will say a few words about, and it is really the first big project, I would say, at least in the pharma, where semantic web technology, so linked data, but this time with very rich provenance, plays a major role and has brought semantic web out of somewhat nerdy environment, I dare to say here, to real-life applications and actually getting into business-critical applications here and there for certain areas of industry. So the topics of my talk is open, always fair. I will explain at length, of course, what fair exactly means, that the fair data. I will say, don't try to make helicopters that dig, and that was mostly pointed initially at publishers, but I think it's also important for this audience to make sure that we have to make research tools now that really serve the typical particular point where you are in your discovery life cycle, and not try to make everything. Because if you make helicopters that also dig, they crash. And we've seen that in many cases. Big data, everybody's talking big data. I will try to make a point that big data is not necessarily better. It's certainly not a goal in itself. The goal is, in the end, obviously, knowledge discovery. That's what we are all after as scientists. And therefore, part of my work is actually what I call data zipping. We try to make data files smaller so that they can be easily transported without losing information. So data publishing is sort of, maybe not for you, but in our field it's a sort of new thing. Data was always sort of put as supplementary data to an article. That time is really over. You know, in a keynote earlier, Carol Goebel said, raise your hand whenever you review a paper. Do you honestly go through all the supplementary data? Of course not. That's 500 pages. So no reviewer has time to really look at them. So we are entering an age where the computer should be able to read our data and judge them, as far as computers will ever be able to do that. And that altogether comes to fair data. And fair, as I will explain later a little bit more, stands for findable, accessible, interoperable and reusable data. And what is needed to reach that for computers, I will say a few words about as well. So that was a very brief introduction. So let's go to the context first. So even at the World Economic Forum, now the last few years, they talk about data as the new currency. Then we have our old good Nelly Kroes, who says in some tweet, data is the new oil. And then, of course, somewhat later, she called it the new gold. And it's not so simple to say, okay, we have currency and data are very valuable, as we also agreed. This is a paper we published in Nature Genetics 2 years ago. But if data is so valuable and data is the new oil, and here it comes close to your field, why don't we have piping? Why do we all pump the oil from the bottom and just spill it in the environment? Why is there no data citation? Why is there no incentive for scientists like me to share my data? As long as we only judge by the stupid journal impact factor, it will never happen. So that is really a very important thing, that the social hurdles to data sharing are as big as the technical ones that you may also be facing. So oil, gold, currency, blah, blah, blah about data, but there is no way we can actually deal effectively with data today, and that's what my talk is all about. So first of all, some scary pictures. The first one on the left, Kees gave me this nice pointer, I should use it, obviously. Otherwise. So this one is very interesting. This is the loss of data if you check the link to supplementary data in top journals over the years. So data was made open by hooking the server of the PhD student to the internet. We call it open, then the guy leaves or the lady takes his server, data are lost. That's terrible. The other thing here is the data increase in the life sciences. And of course, you've always heard the high energy physicists and so on, the astronomers, claiming they had the biggest data. Well, they don't. We have much bigger data, much more complex data, and always tease my colleagues in the eScience Center that although they have terabytes and petabytes as well, their data are actually of the structure. We don't see anything, we don't see anything, we don't see anything. Oh, now we're too late, when the neutrino came past. And we have data that are extremely information dense. Sequencing of genomes and connecting them to metabolomics and proteomics is really highly complex data, and we are doubling the data in next generation life sciences every 6 to 8 months, far outpacing Moore's law, as you can see here. So even for the simple storage, we already run into troubles, and we have to put stuff on tape and so on. And getting an actionable amount of that data available for actual, what we call in silico knowledge discovery by computer, which is essentially what eScience is, we need real new systems and approaches. So again, data, the new oil. I deliberately chose this gloomy picture to summarize the terrible situation that I just summarized. And then I said, look, this is what really is happening. Everybody stores the data locally, they spill over in the environment, and we are a sitting duck in the middle, and the oil is killing us rather than really helping us at the moment. And we have this terrible saying in our field that we ask people, can you get me these data, or did you archive them? Usually they are archived, and then we have the so-called data graveyard. So that is really the bad side of the story. And we have this whole complex data cycle in eScience, where you start obviously with careful design and planning, data processing, curation, data integration and preservation, e-data stewardship and infrastructure, your field largely, and then data analysis and modeling. And that goes on and on. And our aim is twofold. One, get data experts already very much at the beginning here when you plan your experiment so that you don't mess up even in your data capture. And what I will call the data stewardship 5% mantra. Nobody should fund research anymore without a work package on data stewardship, and I will explain the difference with data management, of about 5% on average of the budget. And you can make your own calculations what that would mean for our field of big data if we got 5% of, for instance, only Horizon 2020. That would be already quite something. So finally, before I go into some science, let me tell you why our data in the life sciences are so horribly complex and why we are dealing with very different data from many others. And that is also why the Fairport initiative that I will discuss later was started in the life sciences, not only because we happen to know about it, but also because it's probably the most challenging data problem at the moment. So first of all, obviously, and I'll move, I see the camera has to follow me, but well, that's their problem, I would say. So we have this many different layers. You start with sequencing genomes, then you see how the RNA looks like. And just to give you one example, a few weeks ago we were co-publishing a paper that was in Nature with 95 organizations on it. That's totally crazy, of course. And we showed in that paper, we did the nano publication, the RDF and linked data for that paper, 160 million new associations, the transcription start sites of every gene, where does it start to be transcribed by the enzyme, and it appears to be different all the time. So again, a bit of textbook biology down the drain. And this is all the time that we find new data, we find new insights in the 90% of our genome that we have hardly explored. But anyway, then you get the RNA, then you get the proteins, and then how they interact with metabolites determines how you and I look like. And then finally you go to the cells and the organs, and then the organism, and then even epidemiology. So we have all these obviously have very different technology. Big vendors with gleaming, big machines. They all have their own software. They spit out all kinds of non-interoperable data. And before you can do systems biology, you have to integrate these data through all these layers, which is quite an issue. And then we have all these organisms. You know, you have all this stuff, from virus to bacterium to mammal, and we have so many model organisms, and we don't even know whether we find something in mice is necessarily true in humans or not, as you probably all know. So really, a very deep data analysis is needed to make any sense of all our data. So we need lots of experts that are experts in very many different fields to come together to answer any serious biological question. All the simple stuff, one gene, one disease, has been found. Now it's becoming very, very complex. We have indications that the average number of genes that is regulating one particular part of our phenotype, how we look like and so on, and therefore also diseases, is rather 200 than 1. So very, very complex. And then, of course, our goal of all this research in my field is not just research, is to get better crops, to improve health, or to get all kinds of industrial biotechnology better. So there is also many forms of application. Now, if you look at this picture, you think, what the heck are we doing? Why would we even start creating all these data? Obviously, now we go narrow down to see, can we handle these data efficiently with the technology we have, or that we can develop in the near future, including the whole infrastructure and networking under it that is needed. So let me go back to this slide and tell you about the Open Facts for a minute. That's a project from the Innovative Medicines Initiative that I'm involved in, and it is really having a lot of partners. Now, if you go to the website, I think you see close to hundreds of logos of companies that are now building around Open Facts on linked open, high provenance data, and make their entire application working on semantic web technology. And that was unthinkable even a few years ago. So I put in this slide to silence all criticism, as if semantic web technology is just for nerds. You know, it's not any longer. And I agree, it was not so long ago. Let's put that also. So now we are trying to go and simplify things to the bone. First of all, what is really e-science? Everybody talks about it, and we have even an e-science center in the Netherlands. And then the first director had to spend quite a time to find a good definition of what e-science was. We had a center, but now we needed a definition, so that's also interesting. But to me, it's essentially science that cannot be done without computers. It's not computer science. And what you want nowadays is, in an ideal world, all legacy information, and I don't mean legacy negatively here. This means UniProt, all the proteins, Campbell, all the chemicals, all the databases, all the literature, everything we have ever said so far in life sciences you would like to have access to. I call this, as a good biologist, we always have ohms, as you know, I call this the explicitome. So that's everything we made explicit so far. Wouldn't it be nice if I generated a new data set and it basically would be talking straight away to all legacy information to gain new insight? So this is essentially the oversimplified picture of e-science. You create a new data set. I'll come back later to the point that even that is not always the case. There is now a Nature call saying we will only accept papers in this call that have no new data. You just have to do new insight based on existing data. But assume you create a small data set, you sequence a few thousand people, that's what we call a small data set nowadays, and you want to know what is this association between this strange variation in the genome and Alzheimer. Wouldn't it be nice if you could access all data in the world that could give you insight in this association without having to go to 150 different websites and find out the best query to dig up some of this information to then make one graph in your mind of how this could work? So this is what we have to do. And that's why I always have this metaphor, and this I made for publishers, but I think it's good to bring it. This is what I call the aerial survey. If you fly over this wheat field, you may see that there could be something like a medieval fortress there, which you would never see if you walked into this field. Because when you're breeding, for every gene, there is an average of 90 papers. So if I show the connection to a scientist in the lab between Huntington disease and a new gene, and there is one gene in the middle, and she, in this case, doesn't know about that gene, is she going to read 90 scientific papers about that gene to figure out what the gene is all about? That's terrible. So reading is no longer an option. You have this helicopter view, as I call it. So you fly over big data and you do pattern recognition in big data. Compare it to this finding by helicopter. Now you would be an extremely bad scientist, obviously, if you were sitting in your helicopter and you would just say, hey, there's a medieval fortress there. I conclude, no. So in the aerial survey, it is not enough to just do this. What you want to do after you discover a pattern in big data, genome-wide association, whatever, is you go for deep excavation. And that's the picture I used for that. Here you see people brushing the stones to see how old they are and whether this is really the fortress he thought it was. Now translate this to my field of science. I get this beautiful picture in 2 clusters in all kinds of triples I derived from the semantic web in biosemantics. I will explain what that is. And finally, I want to know why the heck would I believe this triple? It's an isolated assertion in science. I want to know what was the assay used, why, who did it, when, did they use the right reagents, so that I believe their rhetorics, their conclusions. And that's what we always need. Narrative. It's not going to be that all these elements are also captured in RDF and put in the web for the computer to understand. So if you mix up these two all the time, and for example in some publishers, I agreed not to mention too many names, but some publishers would have articles of the future, which I always called the article without future. Why? Because if I'm digging and I'm reading why I would believe a triple or anything in my graph, in the helicopter view, I don't want to be told, look there, a Christmas tree of hyperlinks in my text. No. I want to sit in the train or the plane and I read why I believe this particular pattern that I saw in the helicopter. So quiet, please, when I read. no hyperlinks. If I explore, I'm in the graph. And people mix that up all the time. So how can we go down from this enormous explicitome to something we can manage? Because the explicitome, this is not all of them, but this is one visualization that you would get if you take everything we said about genes in this case only. And Larry Hunter, a colleague of mine from Denver, calls these ridiculograms. There's nothing you can see, hairballs, you know. So first of all, this is not even looking for a needle in a haystack. It's a stack of needles, and we have removed the hay, but still, what do we do? Now, first of all, coming back to this computer metaphor, this helicopter metaphor, you recognize patterns in these huge data sets by integrating all these data. Suddenly, by integrating GWAS data with literature and the protein data bank and UniProt, you see a pattern emerging that certain genes might be involved in Alzheimer's or any other disease. And again, if we think about the number of assertions and associations that we have made explicit, so which are called the explicitome, we made a calculation years ago, but it's not far off the mark, we think by now, that this would be in the life sciences, the red biomedical life sciences alone, actually, already 10 to the 14th individual associations. Now, if you capture those in triples and you want to add provenance, you get an enormous amount of triples, obviously, a lot more than 10 to the 14th, and everybody knows there is no triple store in the world that can nearly handle that. So we have to do something before we can work with these data, that's clear. And I'm not going to wait until you have 20 times faster machines in 20 years from now. There's no way. So what we did is we did the following. We said, okay, if you look at all individual assertions in the web, then we can call them what we now call nano publications. What is a nano publication? You say every assertion, the smallest meaningful assertion, that could sometimes be one triple, like malaria is transmitted by mosquitoes, my favorite old field and example. That's one triple, subject, predicate, object. And you have the provenance, like who said it and when and why. So we separated those two in two little graphs. I won't bother you with the RDF itself under the hood. So you can capture that in RDF and give it a unique identifier as a whole. And now you have a single publication. Treat it very much like you would do any narrative publication. First of all, never change it again once you've published it. So no versioning, nothing. This has been said at this time of the day by so-and-so. That's it. Now, if you have these nanopublications, we would have 10 to the 14th of them in the whole explicitome. Now, if you think about this example of malaria is transmitted by mosquitoes, for example, that, if you mine PubMed, our famous abstract database in the life sciences, that assertion, exactly the same assertion, is there 6,800 plus times. Yesterday it was 6,800. Because everybody writes that again, that's for human language. Wait, the computer in the graph only needs that once with preferably an evidence vector associated. So what we have done for biosemantics, and that is coming to the core of biosemantics, say, okay, we have x times or n times the same identical assertion, and the computer is very good in spotting those if you map everything to UUIDs and not language. Then we have n different provenances, different PubMed IDs, different time date stamps, different authors, so the provenance is really, really rich. But we tune that down to one triple in our graph, and we separate the provenance. To give you some figures on how that relates, if you take semantic medline, which is all the triples that the assertions that the National Library of Medicine in the US has been able to mine from their own asset, then you get, they miss a lot because they don't have a full thesaurus, but let's say, okay, that's the maximum they can get, is 65 million assertions in PubMed, in the abstracts. If you take the whole set with provenance that they deliver to you if you download, it's 2.2 billion triples. That is all the provenance around, it's also triples in RDF. If you take the redundancy out of that set, you are left with only 8 million unique assertions, cardinal assertions. You store the provenance somewhere else, and now the graph is completely clear for the helicopter part, for pattern recognition in that data. So now you have a big zip of the data. And let's take that a little further. if you now go and you take all these cardinal assertions, they all have a subject, a predicate, and an object. Imagine that if you look through the entire biomedical life sciences, we have 50 million chemicals that we could talk about in ChemSpider and the Royal Society of Chemistry. We have about 4 million concepts, genes, diseases, and so on, that we could talk about in the life sciences. We know they exist, we have them in a thesaurus. But if you look through the entire literature, we do not talk about more than 1 million concepts, units of thought, in the entire life sciences, biomedical life sciences. And what you can do now is take all these cardinal assertions and you stick them together with their subject in the middle. And that's what we call a knowlet in biosemantics. So this is the knowlet of Huntington's disease. Everything that was ever said about Huntington's disease, you could also say the mini explicitome of Huntington's disease. This is the knowlet of a gene, one of the 25,000 we have. Both of them could be expressed as vectors in multidimensional space. So you have a matrix, imagine, of 500,000 or so by 500,000 concepts, and they all have a distance relative to each other based on their inner product or whatever measure you want to use. And apparently this gene comes so close to Huntington's disease with all these genes and proteins and diseases and stuff in the middle, attracting the two because they share those concepts, that we predict this gene to be involved in Huntington's disease, even if it has never been mentioned explicitly in the literature. So this is what we call the implicitome. We have predicted for 280,000 genes that they have something to do with a disease. And now we check that with GWAS data that are literature independent. And if we find genes that are predicted in both ways, we think we have a hit. So this is really knowledge discovery with the explicitome. And that is what we want to do. Strangely enough, we started with 10 to the 14th triples that no triple store could handle. Now we have 500,000 vectors that run on my Apple, on my laptop. I won't say anything about PCs, but at least on an Apple it works. So these things come very close now. We report them. And you know what the strange thing is? This paper is now for the 3rd time in revision in Nature Genetics, and the reviewers don't want to accept it. They cannot handle the idea that the computer is better than people in these things. But it is. So imagine the first time that Kasparov was beaten by a computer, the paper about that would be sent to him as a reviewer. He would probably have a lot of troubles to accept it, and that's what happens to us. So we beat the scientists in looking at these big data, and then they say, here's a little thing that we cannot see and so on. So that's a bit of a frustration I am allowed to also put across in a keynote, I suppose. So zipping the explicitome again, summarizing this very briefly, from 10 to the 14th to 10 to the 11th, cardinal assertions. We assume that roughly every assertion is in the web about 1,000 times on average. And then we go down to knowlets. So from a graph to these knowlets. And now it's very well doable. Coming back to how we do this in science is another issue. Because if I now show this to the lady in our lab, we have 120 biologists sitting there. And she is working for her whole life on Huntington's disease. By definition, she never heard of this gene, otherwise she would know it is involved in Huntington's. Now I show this picture to her and she can click on any of these concepts here, and she clicks on the first 3 and she never heard of them because she doesn't have 500,000 concepts in her head. And each concept has 90 articles about it. So she throws it out and says, I cannot handle this. So the real e-science, that we have so much information, there is simply no way to handle that with the traditional systems. So what we are planning to do, I have to make very clear, everybody raise your hand, this is not yet there, it is, future, but it is very easy now to have this. I already had in another keynote years ago at Vivo a mock-up where somebody was in the audience and I clicked on one of these Skype logos and the phone rang, but we are not allowed to have them on here, but the phone rang, was on the speakerphone, and I asked why this gene is so close to Huntington, and the person could answer. So what if I could just call the people that have dedicated their lives to these concepts here, call them together in a Skype call or whatever, and say, why the heck is your gene so close to my disease? And we have, for each person, also a node. So if you take any of you and all your scientific publications, or my scientific publications, I'm in the middle, and these are all the concepts I published about. And of course they move in the same space as the genes and the proteins and so on. So we always know who to call together to solve one of these complicated connections in the graph. And I think that's the only way. Of course the computer should do most of the work, but in the end humans will decide what's going on. So that's again the helicopter. Then you have the digging and all kinds of tools that really make it easier to understand what the mechanism may be behind an association that you found in the helicopter. And this is iterating all the time in modern science. So this is again another way of looking at what you do with e-science. So there is even companies now, one of them is HEAnet, a Dutch spin-off that is very closely working with our university. They bring together all these databases into cardinal assertions, and you can even go to this tool that shows you immediately in the PDF of the full text article where the triple came from. So triples that we already know are projected back into the text, that's where they come from, so you can quickly read. This tool I want to mention also on behalf of Steve Petterfer from Manchester. It's called Lazarus. That's because it resurrects PDFs from the death. And what we can do, we index PDFs that come to the screen, and if we see a sentence that contains a co-occurrence like a gene and a disease or a drug and a disease that we don't know yet in our database, we can make the sentence green or red. We give it to 1,000 students in Leiden alone in the library. They have access to the full text of Elsevier, and they see a green sentence and the button says cite, and we have the sentence, we turn it into RDF, and we have everything from the full text. So it's also a very nice way of mining stuff from the full text without asking permission to anyone, because legally this is just citation, and we are totally allowed to do it. Facts are not copyrightable. So again, digging there, helicopter there. Separate the two very clearly. That's one of the main messages of my talk. Just to give you one final example of how that could work, in a very simple example, but showing you already that you do not always have to generate new data to get new information and new insights. But you can do a lot more than what I just showed you, but that is all still quite confidential. This is done with the tool that I just talked about, the commercial tool of HEAnet called Brain, Biorelations and Interactions Network. So when I showed the tool briefly to one of the most prominent scientists in the Netherlands, Frank Miedema, who is the dean of the University Medical Center in Utrecht, but also heading all the university medical centers in the dean cloud of those, NFU. He gave me this paper that he had together with a whole group here, as you see the authors. And they found the first time the mechanism for something we already knew, that if you have chronic immune activation, so you get all kinds of small injuries, but also inflammations, then, and you're HIV positive, the chance that you're going to progress to disease is higher. But the mechanism was never made explicit yet in the literature. So they set out and they read very meticulously 221 articles. I'm sure they read a lot more than that, but that's what they cited in the review. And they published this paper in a very good journal without doing a single experiment. And if they digged deep and long enough in the literature with the whole group, I still have to go back, this is very new, I still have to go back to Frank to ask how much time did you really spend to find this mechanism, but they found it. And they cite all these articles. So his challenge to me was, okay, if you use the semantic web technology that you just demonstrated, could you repeat this and find the same mechanism out of many different databases? So what we did, we took the tool, it doesn't look nice yet, but okay, there will be beautiful applications around it. You type in the concept inflammation and the concept HIV disease progression, and don't ask me right now, I can explain you how this works, but we compare it with the whole graph, and we say we predict with 80% security that these two things are highly related, and we have a lot of connections in the graph, so better have a check. So then what you do, you go on, if the thing goes on, and you can do this for all kinds of other things, by the way, as well. So we predict in the graph that we have now 44,000 new protein-protein associations. One of them was published already to be true. 280,000 gene disease, etc. So you can do drug disease, and so a lot of predictions are intrinsic to this graph, the implicitome, as we called it before. If you now check all the paths between the two concepts, you see there is no one here, because then there would be direct co-occurrence in the literature. There was no concept in between. And then you can browse through them, and one of them I picked here is this gene affects inflammation and is associated with HIV disease progression. So it's a sort of in-between concept. And the funny thing is that we found a lot of those connections that were actually not even mentioned in the Miedema paper. And then we don't know yet whether they discarded them as irrelevant or they still missed them. Also, we found others that were in the paper, like another via apolipoprotein E4 or via multiple steps. And if you go on, you create this whole picture here, and you see that if you try to drag these two concepts apart in the concept space, they bump back together. The system tells you they are related, and this is how. So this is reproducing in 4 minutes what I suspect to be months and months and months of reading, and it is without any further experimentation. So that is the future of science. People either create a small data set and want to get that data set reviewed by all legacy information. Remember my very first, very tiny picture of what e-science essentially is. Or they do these kind of things. Now, that has resulted in a editorial in Nature in March, which was a direct result of our Fairport meeting. That will be my final point before I end. In January in the Netherlands, where Miles Exton, the editor of Nature Genetics, was one of the participants. And he decided, as his contribution to show that data can be reused, fair, he said, okay, I will have a call for data analysis papers where you don't have to do any new experiments, but you report testable hypotheses. And you have to take Elixir or the Big Data to Knowledge initiative, and both are collaborating on this FAIR principle that your data should now be published in a findable, accessible, interoperable, and reusable format. So that is the Fairport initiative to make this all happening. And in fact, this is all based on linking data, not so much to the classical ETL, extract, transform, and load, and put it in another non-interoperable system. So we are very much into linked data and say, you either link and reuse, and then you can have a whole lot of levels, 5-star, 1-star, but everything should be fair, and I will explain what it is. Or archive and lose in the old way, you file it somewhere, you never find it back again. So forget about this one. And what does really make data fair then? As I said, and I will go quickly through the 4 points, what makes data fair is really this: findable, accessible, interoperable, and reusable. And you see here that obviously open is not the right term anymore. And when the European Commission started their first pilot, they lost immediately the biomedical community, because we said, oh, open, our data cannot be open. Patients, the most perfect excuse, not to share your data, or patients, obviously, or people, privacy, So we said, okay, findable is important, because if I hook my server to the internet, it's open, but my data are not findable. The computer doesn't know the identifiers, all this. Accessible is not necessarily open. So every nano-publication, or whatever form you choose, has a license. Some can only be seen by the white coats in LUMC, in our own hospital. Some are published in a way that everybody can see them. So data can be fair without being completely open. It should be interoperable and reusable, and very importantly, both for humans and computers. Otherwise, it's still not fair enough for e-science. Now, how can we achieve that? We learned a lot from the internet. You have this hourglass idea that you probably know much better than I do, where you have maximum degrees of freedom for the application layer. You have minimal things in the middle. You will see that this is essentially IP and TCP and so on. And then you can also go very widely with the producers. The scientists are both producers and users. And I deliberately left German on these slides because I got them from Peter Wittenberg from the RDA, and he had made them in German. I said, why not leave that, because multilinguality is also an issue that can be solved by UUIDs and persistent identifiers for all terms. So he said, if you look at the hourglass model of the internet, you probably would put IP here. And if you go and translate that to data, a web of data, so the internet for data, you basically have the persistent identifier in the middle, and then lots of degrees of freedom what you do with it. So what they are doing at the moment, they've started this thing in Geneva, which they called the Digital Object Numbering Authority, DONA, and they want redundant places in the world where you can just come with your data set and get a PID for everything in there, like every gene, every protein, every city, every university, every person, and we enable them via ORCID and Vivo and all the enablers that are already doing these persistent identifiers for all entities, all concepts in the world. And obviously that has to be around the world, because you cannot have a single point of failure, and we try to get this going between Europe and the United States without fighting about it, because this is a global thing, and it's not only Europe and the United States. We also go to China and to Brazil very soon to get this going. And we have a next meeting, which I would all recommend you to go, in September in Amsterdam, the 4th plenary of the RDA. And there I will have another keynote, but also Robert Jan Smits will talk about how the European Commission looks at this. And in 2015, there is a meeting of the Global Research Councils, and that is our self-inflicted deadline, as we say, to try and get this up to the level of the Global Research Council meeting, to say 5% for data stewardship. And that's what I want to end with, one or two more slides, but basically saying, what is the difference between data management and data stewardship? There are more and more funders that say, you need a data management plan. But it still sounds to me, and that's good, of course, very, very much better than just producing data and then saying, oh yeah, we forgot to budget for keeping them and for changing them and exchanging them. But data management still suggests to me that when the project is over, your responsibility is over. That's not true. If they are reusable, we need to keep these data sometimes for more than a decade. And in some cases, you can more cheaply resequence a person nowadays than storing his genome for 10 years. So there is all kinds of questions beyond the project. So all these enablers are going around the world, and you will see RDA here and so on. I don't know whether I put TERENA here, I don't know. It's an old slide. And one of the things is, let's not fight about this between continents, but do this all together. And one of the things we do in the Netherlands, in Europe, is of course do this via Elixir. I don't think I have to explain Elixir to many of you, but it's one of the S3 infrastructures, and it's really the one that tries to underpin all the others for the data. So that's very much where it belongs. I'm pointing there. Nicholas is the director. This is Søren Brunak and Janet Thornton from EBI. And we have nodes in many different countries, and you see I'm the head of node in the Netherlands. This is all endorsed by the European Commission, and each node has these particular highlights, and we are really pushing a lead in the Netherlands as data interoperability and exchange, which is what I just talked about largely. Obviously, you need a lot of compute and storage for that, and in DTL, SURF, SARA, and SURF in general are co-founding partners, so they take care of this part. Obviously, we don't do that, so that's why don't ask me questions about that. We'll point you to one of the SURF people in the room anyway. So then, training and education is very important. The Economist says that we will have 180,000 shortage of people that know how to deal with big data very soon. And I would like to finally end with a rather challenging statement, because I was asked to give some challenging statements at the end. And I think it's really terrible that data are treated the way they are today. We just lose them, as I showed before. So I think a number of people, or practices rather, should be scandalized and really put in the middle of the square of the village and say, never again. One is supplementary data. It's a terrible system that was a sort of interim solution. Forget supplementary data, publish your data, and have a supplementary narrative to describe how you got there and how you interpreted them. That's one. Scandalize people that judge scientists on their journal impact factor. In jail. Funding research without a good data stewardship plan, terrible. You know, lose your job. Ignore old metrics. We now have all the tools to check data citation, to see what social media do with my article. And when I was very proud that my value of data article was tweeted more than any other Nature journal article, my dean almost fired me because he found out I was on Twitter. You know, so really, it doesn't help at all. So unless the deans help us, we will still not get anywhere. Because why would I share my data? I have no incentive. And all this is obstruction of discovery, which then obviously impairs knowledge sharing. In our field, I can claim that will cost lives. You know, so really slowing down science by not being prepared for big data and not being able to zip data into manageable format now and not wait until you get to 10 to the 14th triples is what we need. And we should all stand up with one voice and tell the funders, no further science without good data stewardship. So that was my plea for this audience, I think. Thank you. I suppose we have some time for questions?
Yeah, I think so.
At the reception, there were at least 2 people that said that they had a question for me, so don't shy away now. There should be questions. Or I did answer them in the talk, obviously, but questions, please. Kees.
My name is Kees de Laat, University of Amsterdam, and actually program chair of this September thingy where you will be talking. But I have a more structural question. So all the universities are now wrestling with the problem of data stewardship, and every university itself has this grand program, including their library people, because you know books go out and you have the people, so you need something to do with them. But it seems to me like a scattered effort. What would you think would be a very good national program for the different nations, just like they treated computing, like they treated storage, like they treated networking? What would you recommend as national programs for data stewardship?
Okay, first of all, I'm glad that after this talk you still think I will be talking in RDA. You didn't change the program right away. But okay, but I'm totally in agreement with the scattered approach, and obviously librarians, with all due respect, are not necessarily the best people to lead this thing. They're just forced by the deans to do something about it, and they don't know what to do. I think this donut thing that I mentioned is going to be extremely important, because if we define the minimal standard that you need to make data interoperable, and for example you say whatever element you have in a graph or relational database or whatever system you use for your data publishing or your repository, as long as every data element and every provenance element is computer resolvable to a persistent identifier, so the computer knows what you're talking about, and therefore also people know what you're talking about, then that is the thing to enforce nationally and internationally, not RDF or relational database or XML or any format. So I think the success of the internet was that, you know, if you don't keep your TCP/IP rules, forget it. But because that's so minimal, it works. So for me, the only way to bring those scattered efforts together is to find the absolute minimal standard they can easily adopt without telling them a whole list of things they have to comply to. You Dutch, you know, we will never do that. So, and biologists are the worst of all. They would rather share their toothbrush than their gene name, so as we say. So,
hi, I'm right here.
Hi.
My name is Greg Bell. I work with Lawrence Berkeley National Laboratory in the U.S. So I wanted to thank you for a fascinating talk. And a question I have is whether the I've noticed that in our environment, resistance to the techniques that you've described sometimes come from people and scientists who believe that you are reducing the role of hypothesis and elevating the role of correlation. And they're worried about something like hypothesis-free science, which seems to them like a contradiction in terms. And I wonder if you're encountering similar kinds of resistance and whether you think that you are recalibrating the relationship between hypothesis and knowledge discovery.
Well, I mean, very nice question, of course. This almost cost me my job and my papers because people say exactly that. And we say in e-science, the data throw the hypothesis at you. It's not that you don't, of course you have open discovery and closed. You either, in the past you were reading and reading and reading, and then you came up with some hypothesis, but in fact you did pattern recognition by reading, you know. And I have a full-time student on chaos theory from Santa Fe Institute now in Leiden, and he's showing more and more that all knowledge discovery in the biomedical sciences over the last 20 years took place at the percolation point between chaos and order. So the only thing we do for decades already is finally we see the pattern by reading. Now we finally see the pattern years before. So this Nature paper I was so frustrated about, one reviewer rejects it 2 times by saying I took 6 of the predictions, hypotheses in fact, and they were made purely based on PubMed abstract. But I digged for a week and I found supplementary data, I found microarrays, I found this, and you know, all 6 are true, but they were actually somewhere already explicit. So these guys do not really predict anything. Well, I told Miles, give me the name of the person, I'll make him a co-author of the article because it's the most prominent reason to accept the article. We predicted 6 out of 6 correctly on PubMed abstracts, and the explicit information was not to be found in the training set for the computer. So this is extremely powerful, but the silverbacks, who always did it by reading, are reviewing my grants. Big problem. It's changing. There's no way out. If you think you can do still biology by reading, okay, be my guest for a few more years, but most of them retire soon, so that's okay. Including me, by the way. So.
Thank you. Kind of a follow-on question for that. Something you said earlier really resonated with me, and that was that the social hurdles are as difficult as the technical hurdles around this big data. And absent the kind of provocative solution you suggested at the end of your talk, what can we do as a community to kind of move that conversation forward and get people to understand that we're really, by not sharing this knowledge, we're wasting data, it's the equivalent of burning books?
What can you do? I mean, of course, first of all, I know this field now, and people use any argument not to share their data, and sometimes they have very different reasons than they say, but anyway, I think in your case, we say, of course you want us to share data, then we need your infrastructure, and now we need to give you more money. But I think that really there is one strong correlation. Over the years, I've also been working for a few years at the European Commission, between getting money for something and speaking with one voice. Look at the CERN people. They got this crazy thing, and you know what it costs? Because maybe in 3 billion years, we are hit by something. So the thing is really that if you are able to make a comprehensive and a consistent story with a whole group, and you go to the right people, like we are now trying with the Fairport to the Global Research Council, then you get your money. So as long as we are ourselves a scattered community, and as the previous speaker suggested, we are contradicting each other, these crazy guys are doing no hypothesis, forget them, dangerous. We're the silverbacks, we're sitting on our rocks, we can still read. Now, as long as we have that, it will never change. If we all start to boycott, you know, the journal impact factor, and if we all start to speak with one voice and say we need 5% for data stewardship, and that's the whole cycle, not only data publishing, then the money will come. And I see it already now that every single research council, including the European Commission that I'm talking to at the moment about this, are very receptive. And in Brussels, there's even this idea to make the data stewardship plan part of the proposal, so it's a deliverable. So now you can spend money off your grant to write a good one, and you need a work package leader for it, and it has to be a credible person. So I think if we speak with one voice and we make white papers, then okay. And I cannot resist to say that one of the research councils, I won't mention names, where we sent a data stewardship document, a white paper, screaming, lost it. So they actually lost the paper, so that was a bit of an irony. But I think we can exchange policy papers and white papers and speak with one voice with your institution. So join the Fairport and speak with one voice. Then.
Hello, Christian Kai from DFN Cert.
Okay.
Thanks for the very interesting talk. I was wondering, while I was listening to your talk, you have all these predictions, and as far as I gathered, this is actually quite new, and you had one example in there where one of the predictions was validated by different studies, and you had the example before with 6 predictions out of 6 being correct or being somewhere implicit in the literature. Did you have any that were invalid, or do you have a feeling of how large your true positive and false positive ratio might be?
I mean, you sound like my reviewer. There are no false positives. Everything is related to everything, as we know. If we take 25,000 genes and the helicopter goes high enough, they are all related because they make us human. It's not a matter of false positives, it's a matter of actionable knowledge. Where in the graph you go down and you find a pattern that you can act on. You can find a drug or a gene. So I hate the term false positivism. I've been publishing about it many years when we did text mining. And text mining has false positives, obviously. You just you think something is there and it's not there. In GWAS, genome-wide associations, there are no false positives. There is only a level of correlation between a genomic region and a phenotypic association. Same here. So in a desperate way to get this one reviewer off his rock, we invented the term LWAS, literature-wide association studies, rather than text mining or whatever, because you just show associations. There's nothing true or untrue. The question is, if you see a strong association in the literature and you find the same association in GWAS, and there is patient records that suggest the same thing, you have a hit. And that is not non-hypothesis driven. You're still in search for hypotheses, but they come from the data. And then you validate them. So you still validate your hypothesis in the lab. The only way the hypothesis came from your mind by reading in the past or talking to people at conferences, well, you cannot talk to 10 to the 14th people. Even I can't. And that means you need these other ways to generate the hypotheses. So no false positives. Thanks for the question anyway, because that's my preaching. So I saw another one there in the back there.
Hello, Victoria Rao, Elsevier. Thank you very much for interesting presentation and sparkling discussion. I was just wondering, as a part of the stewardship plan, do you foresee publishing the data sets along with the paper itself? And if so, do you believe that publishers provide the adequate platform for that? Thank you.
Yeah, I have been talking very intensively over the last year with Elsevier, with Olivier Dumont and Gabi Appleton and IJswan Jan. Actually, until last Monday, we were meeting the 4 of us, so I know that Elsevier is extremely interested in data publishing, and I'm very happy to say that they said that they would never have the intention to put the data behind the firewall, and I think their text could still stay behind the firewall. That's for digging. So I believe that publishers, that's not just restricted to Elsevier as the biggest one. There is an enormous market for data publishing coming up. So in that sense, Nelly is right. It is the new oil. We estimated that the whole global market for data stewardship may be in the order of 50 billion per year. So there is a lot of business there, but not on publishing the data. That's, you can do that profitable and like you do open access publishing. And it's completely normal now that people put $1,000 for an open access article in my grant, so why not for open access data? So there's a business model there. But the big money is in clever tools around the data, that do clever stuff with the data. So one of the things I discussed with Elsevier, for example, is publish all scientific claims from Science Direct in the cloud, open access. They are isolated associations. One of the reasons why my library in Leiden is trying to get not rid of Science Direct, but is, getting more and more skeptical about 1,900 journals. We never read more than The Lancet and Cell anyway. But if you think back to the helicopter, the computer will now dictate which journal to read, because I don't know where that triple comes from that now finally makes this connection between two clusters. And maybe I never saw it because I never read the remote journal of strange diseases, So the thing is that if you look at the publishers that are right on their path to hitting the iceberg of open access publishing, where there is not such a thing as 39% profit, they can find very, very, very nice new business models on added value around data. And they are very interested, I happen to know from Elsevier, but many others, that really Ron Moped says data as a business is the new tagline. So here we go. But then we need to build the infrastructure and to share these data openly. I think it's easier now to convince Elsevier to make the data open that they publish than the scientists. Because why would I do it if I get no incentive, it cannot be cited, and if it is cited, my dean doesn't care? That's the big hurdle. Again, coming back to the social hurdles and not just the technical hurdles, because we can do it now, technically. And as I said, for publishing, you publish the data and you have a supplementary article that says, this is how we did it, if you want to know. But the data are more important, well, not more important, they are in a totally different league. And supplementary data to an article should be forbidden by law.
Thank you.
Thank you.
Thank you, Barend, for this very interesting.
Thank you.
Very interesting, a bit controversial, so it's the type of speech we need. Okay, thank you. Before letting you go, I have to give you some information. Oh, I have to push that. Perfect. So, just to recall you, there is an opening reception. It's not very far from here, just it's the same building, so it will be in the hall here. So you are expected at 6:30 today, but don't forget your badge, because otherwise you cannot enter in the building. There is I don't know if you have seen it, a conference app. You can download it from Google Apps and iPhone system also. It's very efficient and you have all the information, so please try it. Network access, I suppose you are all on Ethereum, and so I don't have to repeat that. The demonstration will be done at two locations, Demo A and Demo B area. They will start every day during the breaks, so please check the schedule. Poster presentation, as usual, we have a poster competition, and so it's the reason why I've put that yellow sticker on my hand. So you have it in your badge, or you did receive it with your badge. So the idea is that in order to vote for the best poster, you just have to put on the poster. But just, no?
Hi, sorry to interrupt here.
Yeah, I made a mistake.
Just a tiny mistake. The sticker in your badge is for voting on the best student poster. So the student posters are on the exhibition area on the right side, and you can put the sticker next to the poster on the paper.
Oh, on the paper. Okay.
And it can be done until the end of the Wednesday lunch break. Thank you.
Sorry for that. As usual, we also are a social community, and so you can tweet and use the blog in order to give some feedback or your ideas or any reaction on the conference. And last, but not least, we need your feedback. So even if you are here only for one day, please put your feedback on the system. You normally should have received an email with login in order to be able to use the system. So please do it. We need it. We see that every year, too few people are really feedbacking on the quality of the speech and the conference. So without your feedback, we cannot improve the conference. So please do it. And so, last but not least, I have to thank the sponsors. They are here expecting you, so please visit their booth and thank for them for supporting us. It helps us to really organize this conference and put everything in place. So, thank you very much for your attention, and now you have some times for, I think, a coffee break and joining the other session. Thank you very much. Bye.